Hello, in this video we're going to talk about on how to get the critical constants in the Berthelot equation of state. The Berthelot equation of state strongly resembles the van der Waals equation. And by that, we should be able to talk about the critical constants. At first, we must find the critical constant for volume. So, we must first rewrite the equation in a more suggestive form so that it would be easier to take the derivatives. So this is the rewritten equation that we're going to use. First derivative of this expression from the respect of volume, as you can notice that in here we have a function of z, which we'll call u here, so that the derivative of u to the minus 1 is minus u to the minus 2, and then we take du dv. But since we have a linear v here, so in here it is just equal to 1. So for the first expression, we get minus rt v minus v, the power of negative 2. Then we have a v to the minus 2 exponent here. So the derivative is going to be 2v to the minus 3t. We have 1 in the front, so that it gives us 2av to the power of negative 3 over t. This then gives us the first derivative that we're going to use in order to get the second derivative. Now we take the second derivative by using the properties of derivative of powers of a function. So we have a 2, we have a 2 here, minus 1 gives us a plus 2 here, a positive 2 in front. The minus 2 now becomes minus 3. Then for this particular term, r minus 3 multiplies with 2 so that it gives negative 6a over t. Then the negative 3 here becomes negative 4. Now we got the both derivatives so that at critical point, both first and second derivatives of pressure with respect to volume will be equal to 0. Now, first we solve the system of equations by setting two equations equal to each other because they're both equal to 0. To do this, we should solve each of the expression in terms of RT squared. First derivative. In order to do so, you must first add RT v minus v squared in both sides. So we could have this expression. Then, you could rewrite the fraction. You could rewrite this as fraction so that it would be easier to do algebraic manipulations. Then after you rewrite it as a fraction, you must first cross-multiply it in order to isolate RT. Next is that we'll multiply both sides in terms of t so that we'll have RT squared. Now, take note of this equation as it becomes our equation 1. Now we move to the second derivative. So this is just the same on how you got the first derivative. So you multiply both sides by 6av to negative 4 over t so that you'll have this expression. Then rewrite as fraction so it will be easier to do algebraic manipulations. As you've done rewriting it, you must cross multiply in order to isolate RT. Then we divide 2. You should divide 2 in both sides so that it would cancel out 2. And 6 divided by 2 is 3. Then we multiply both sides by temperature so that we should get RT squared. And this is our second equation. Given that the first equation and the second equation is equal to 0, so one could say that equation 1 is equal to equation 2. By doing so, you could cancel like terms. You could cancel v3, v4 with left with vb squared, b minus v squared to v minus v cubed, and a, you could cancel all of them. Now, the next step of this one is that you should distribute 3 to v minus b. Then, we multiply both sides by v so that you could remove the denominator v. Then afterwards, use algebraic manipulation so that you could isolate like terms. And by doing so, now we've reached the conclusion in solving the critical constant of volume. We're going to solve for the critical constant of temperature next. First, just like in volume, you should rewrite the equation. After rewriting the equation, you should get the first derivative of pressure. When you get the first derivative of pressure, just like in volume, you should cancel out RT, rewrite as fractions given this expression so that it will be easier to do manipulations. Then afterwards, you should substitute the value V, Vc, which is 3V. Then simplify it by using that 3 cubed is 27 and B cubed is B cubed. 3B minus B is 2B squared, so it becomes 4B squared. Now, we multiply both sides by 4B squared T. By multiplying 4B squared T in both sides, we should get a product of 8AB squared divided by 27B cubed is equals RT squared. First is that 4B squared should cancel and T would be squared because T times T is T squared. Then 4B squared, the T would be cancelled and 4B squared will be multiplied here, so it becomes 8A AB squared. Next is that we would simplify by cancelling B squared to B cubed, given that it will cancel the cube and it will only be left by B1. Next is that we divide both sides by R, so that the R in RT squared would cancel, leaving us and isolating us with T squared. Then, took the square root of T in order to get the critical constant of T. Basically, this is the critical constant of T, but we could simplify it further. But take note, we would use this equation later in order to get the critical constant for pressure. Now, by simplifying this, you must first use a prime factorization of 8 because 2 squared is 4 times, so is equals 8. 3 squared is 9 times 3 is equals 27. Then, we would be able to remove this to become a coefficient, remove them under the radical, hence giving us the temperature constant of the critical values of temperature. By getting the pressure critical constant in the Berthelot set of equation, unlike the temperature and the volume, pressure, the solution remains as it is, the equation remains as it is, so that you could just substitute the temperature temperature constant, the temperature critical constant, and the volume critical constant. First is that we substituted the temperature critical constant, that's what I showed earlier, the square root of 8a over 27 Br, and 2b for, it became 2b because Vc is 3b. So 3b minus b equals 2b. Then I just switch here so that it would be easier to understand. This is just the same, but 3b squared is 9b squared. Then substitute the Tc value. And then what we're gonna do next is that multiply in both sides the temperature, the critical constant of temperature, which is 8a over 27, square root of 8a divided by 27 Br. By this, this would cancel out, and square root divided by square root times square root would cancel out the square root, so hence giving that there is no square root here. Then we would simplify by canceling r. R has been cancelled. B did not cancel because they're both in the denominator, so it became squared. And 8 divided by 2 is 4. That's why it became just like this. Afterwards, we're going to find the LCD. So the LCD of this is 27, so that this expression here should be multiplied by 3 over 3, so that it will become 3a over 27b. Hence that if we combine both of these to simplify it further, it will become a divided by 27b squared. To sum up where we have been, pressure PC square root 8a over 27 Br is equals a 27b squared. So in order to cancel this, we must first multiply both sides by the reciprocal of t, which is square root of 27b or 8a, so that it would cancel and it would leave this expression, leaving PC behind. Afterwards, we could use the prime factorization so that it would turn out to be just like this. And then we remove this to become a coefficient, and we remove them under the radical. Then we will simplify it because 3 divided by 27 is 9 times 2 becomes 18. So here we have this expression. After this, we're going to use a algebraic notation that means that x is equals the square root of x squared. So by means, we should square all of this and put it in the square root. Just like that. It's like the same value, but it has a different outcome and such. And after this, we're going to compress both of these in a single radical. Then we simplify it by canceling like terms. So a squared over a, the squared will cancel, this would cancel, this would cancel, and this would cancel, giving it a 3. So what left is a, also 648 divided by 3 is 216. Next up is that we multiply the denominator and the denominator by 2. Afterwards, that 432 gives expression of 144 times 3. Then gives us the expression of 144 times 3. Then we would use prime factorization of 144. So give it as 12 squared times 3. Then, by saying this, we could now put out these two out of the radical, giving us this notation. So this is the critical constant of pressure. In order to do the reduced form of the Berthelot equation of state, first you must recall the critical constants of BC, TC, and PC. So first and foremost, what you're going to do is that expand Vm to Bc times Br, which is critical volume and reduced volume. Once you expanded those in the given equation, substitute the values of Vc in the equation, which is 3b. Substitute. After I substituted the values, you simplify it so that it will be easier to understand. Then isolate b by using algebra, like combine like terms. Isolate b, 3br minus 1, so on and so forth. Then in the second phase, it's just like similar to volume, that we expand temperature to critical temperature and reduced temperature. Then substitute the values into the equation. Given that the critical constant of temperature is 2 over 3 square root of 2a divided by 3br, as you can see, the other one here is a reciprocal of it. It is a reciprocal because the t is in the denominator. Meanwhile, the t here is in the numerator. After that, we could use the expression of P is equals PR times PC, where you could divide both sides by PC to get the reduced pressure. Then, since we're going to use this one, we're going to have the reciprocal of PC. Since it's under the numerator, we're going to switch it up. So then, we're going to distribute the pressure, the critical pressure into this equation. We're going to distribute it. So, distribute this into the given bracket, given that 12 times 3 times 2 divided by 3 is 8. And we'll use the algebraic notation that square root of x plus square root of y is equals square root of xy. So that 3 times 2 is equal to 6. 2ar times 3br is equals 6br. The a will cancel though. And also, it will also substitute in the other side, in here, which is 12 times 3 divided by 2 is 18. Thus, 3 times 3 is equals 9br4. 4a squared, since both are in the denominator, it won't cancel out. And this will just still be the same. After you distributed it, this is the distribute form here. After I distributed it, we could simplify it. We could easily simplify it. Like cancel out the 6. When you put b inside the radical, it becomes b squared. Square root of b squared is b cubed, so it'll cancel out. When you put r into the radical, it will become r squared. When you put it there, it will become r squared, and it will also cancel. What's left is 8 tr 3VR minus 1, which is this one. In here is that the square root of 9 over 4 is equals 3 over 2. Then the remainder of 18 and 9 would leave us this 3. Then, when you put BR inside, B squared inside, it will become B to the power of 4th and it will cancel. When you put A inside, it will become A squared and it will cancel. R will also be cancelled, leaving us the expression of 3, BR squared, and TR squared. Hence, this is the reduced form of the Berthelot equation of state.
Good morning, everyone. Today, I am going to derive the critical properties from the Dieterici equation. So, at the critical volume, the term round P over round Vm is equal to 0. So, we have 1 over P times round P over round Vm at the critical volume is equal to negative 1 over Vc minus B plus A all over RT Vc squared. So, by definition, this term is equal to 0. Now from the right side of the equation, we can get a new equation or relation, and we name this as equation 1, which is A times Vc minus B is equal to RT Vc squared. Now going back to the equation, to this equation, we differentiate both sides with respect to Vm again, and we get this equation. Now by definition again, these two terms are equal to 0. Oh, sorry. I mean these two terms with at the critical volume is equal to 0. Now from the right side of the equation once again, we can get equation number 2, which is 2a times v minus b squared is equal to RT Vc cubed. And dividing the equation number 2, this one, to equation number 1 over here, we get 2 times Vc minus b is equal to Vc. And solving for Vc, we can get the critical volume Vc is equal to 2b. Now to solve for the critical temperature, we use the formula of the critical volume to substitute Vc in the equation number 1. So if you remember equation 1, it's given as A times Vc minus b is equal to RT times Vc squared. And substituting, we know that Vc is equal to 2b. So A times 2b, because we substitute Vc, minus b is equal to RTC, because we're solving for critical temperature, times 2b squared. So AB is equal to RTC for b squared. And isolating TC, it gives us the critical temperature which is equal to A all over 4RB. Now lastly, to calculate for the critical pressure, we use the formula of critical volume and critical temperature and substitute it to the rewritten Dieterici equation. So we have PC is equal to RT all over 2B minus B times E raised to negative A all over R, and substitute TC with A all over 4RB times 2B. Sorry, this 2B should be in the denominator. It should be R times A all over 4RB times 2B. So the variables, cancelling the variables, it will give us PC is equal to RTC over B times E raised to negative 2. So PC is equal to RTC all over B E squared. PC is equal to R, substitute T, TC. So R times A all over 4BR all over BE squared. And cancelling R, we will get the critical pressure PC is equal to A all over 4E squared B squared. And here's a summary of the critical constants of the critical pressure, critical temperature, and critical volume.
So we are going to perform the reduced form of Dieterici equation. So first we have the critical constants. We have the P sub C is equals to A over 4E squared times B squared. Then T sub C is equals to A over 4 times R times B. And we have the volume critical constant is equals to 2B. And we recall the Dieterici equation, which is P is equals to RT times e to the power of negative A over RTV over V minus B. And take note that V represents the molar value. Since the volume is equals to the critical volume, which is equal to 2B, we now substitute 2B to the volume, which gives us the new equation on the right. And we can factor out the b in the denominator, so we can have a simplified form of the equation. So after we factored the b in the denominator, we have the new equation in the right, which gives us the b times 2br minus 1. Next, we replace the T temperature with critical constant T, which gives us this new equation in the right. We can now cancel the R with R, A with A, and RB with RB, including the 4 and 2. After canceling, we can now combine the 4B with the B, which will now form the new equation in the right. Now we can substitute the P with critical constant pressure. We apply the reciprocal form of P sub C. Then we multiply it with the equation. Then we can apply cancelling, which leads to our reduced form of Dieterici equation on the right.